Okay, welcome back to part 8 of the lecture, if I'm not mistaken. Right, so previously we looked at a single slit experiment, right? Wasn't a double slit experiment, okay? There was a typo, right? So it was a single slit experiment whereby the Veritasium video showed you that as you close the gap, which is the slit width, right? As the slit width shrinks, the uncertainty in x becomes smaller, therefore the uncertainty in momentum must become bigger because they always must multiply together to be bigger than h, right? That is Heisenberg's uncertainty principle. Now, so that was for light, all right? So for photons, all right, that was the video for photons. Does this happen for electrons, right? The answer is yes, all right? So we can look at this familiar diagram we've seen in quantum 1, all right? If we look at this diagram, the electron gun is going through slit 1 and slit 2. This is a blown up version of the original diagram you saw, which was like that, okay? So I'll try to explain this diagram a little bit more in depth. Right, so let's look at the Heisenberg uncertainty principle first applied to this diagram. All right, if you have a look, the first thing we want to talk about is really what happens when this slit, for example, this slit 1 and slit 2 So if we just fire through slit 1 only, that means let's say I close slit 2. Right, so if I just fire through slit 1, right, I'm firing through one slot. All right, and this is the distribution function I will get from the electrons going through this slit, right? So that means the electrons as I come through this slit, I will hit this part very often. So this part, if the detector is placed here, you detect a lot of electrons hitting, right? Then this part a little bit less, this part a little bit less, and so on and so forth, right? So if I go and count the number of electrons that hit the detector on this plane, I can sketch this graph over here for P1. Okay, so I hope you understand how I physically or empirically get P1, the shape of the graph. Right, Heisenberg uncertainty principle says that if I shrink this gap, which means I make delta x smaller, right? If delta x shrink, my delta px, which is in this direction, must get bigger, right? So that means instead of having the graph that looks like that, all right, and this is already the chi-square graph, all right, so that means this is already the probability distribution function, all right. What will happen is that, oh goodness, what is happening? Sorry, click something wrong, not sure I clicked. Right, so this is already the probability distribution graph, all right, and now if I shrink delta x, right, what will happen is delta p increase, and that means that the spreading get bigger. Right, so the graph will look something like that. Right, so that means instead of only hitting this part, maybe I will start to hit this part because delta p increase. Right, so I increase the uncertainty of the uh, momentum in this direction. Right, so in this direction, which is the same direction as x is being shrunk. Alright, so that's the idea behind Heisenberg uncertainty principle applied to single slit, similar to like for electron, because as expected, they exhibit wave particle duality. Right, so what's interesting about this diagram is a lot of other stuff. Alright, so I'll just explain the other stuff as well. Alright, you realize that if I close 2 and only let the electron pass through slit 1, I'll get this graph. If I close 1 and only let the electron pass through 2, right? So if I close 1 and only electron pass through, I'll get this graph, right? Then if I open both 1 and 2, I will get this graph. Okay, so you will see that number 1, this is a bit weird because if you think about it, if I close slit 1, I get this probability distribution function from slit 1. Sorry, if I close slit 2, I get this probability, this amount of electrons hitting this position, right, at somewhere near the slit opening. If I close slit 2. If I close slit 1 and open slit 2, I get, try and draw another color. This amount, can you see, because it's from this graph, right? So this amount of electron passing through from slit 2. So if I open both, theoretically, it should be a sum of P1 and P2, right? So you see this part plus this part should sum to somewhere here. But then it is 0 if I open both. Okay, I try to repeat. If I open slit 1 only, I get this. Right? So this you can think of it as number of electrons that hit the screen. So it's highest here, it's a bit lower here, and a bit lower here, and it tends to 0 here and here. Right? So very few electrons hit the screen here and here. And you extend some more, it's just 0 lah. Okay? And then if I close slit 1 and open slit 2, I get this graph. Right? So this graph over here. Then you can see that, I also got electron from slit 2 hitting the position here. But if I open both at the same time, it becomes 0, right? You can take this as 0 lah, very near 0 value. How can that be explained properly? Right, obviously, when I sum P1 and P2, right, I'm assuming the electron behaves like a particle, alright? But in reality, we know that electrons exhibit wave-like behavior in this experiment, and therefore, we need to think of this more like a wave function. That means the electron exhibits a wave function, right? The exact wave function equation in this case, you don't need to know, right? It's probably pretty complex, and personally, I also don't know what's the wave function in this case, all right? So if you think about it from a wave function perspective, right, then what actually happens in this case where both slits are open, right, is that when the electron pass through number 1, the wave function is called psi 1. And if the electron pass through number 2, the wave function is called psi 2. And as they hit this region over here, right, the probability density function, which is actually this one, right? So actually this one should be written as psi 1 plus psi 2 squared, because this is the new wave function of the electron passing through both slits, right? And that will mathematically produce this probability distribution function, which correspond with the empirical data that we collect, that the electron here actually barely hits here very often, hits here very often, barely hits here. And this part can only be described by destructive interference, and this part can only be described by constructive interference, right? So that's what it means by we try to think of the electron like a wave function, right? And for me to produce this nice interference pattern, because we think of the electron as a wave function, the interference of the wave function 1 and 2 will give me Ci here and Di here. Okay, mathematically it's represented by this, right? The original wave function of P1 and P2 is actually represented by this and this, right? Which is actually psi 1 square and psi 2 squared. Okay, all right, this part I know is a little bit difficult, right? Again, I'll just give you a skinny part, that means a general overview of what's going on here, right? To explain why these two graphs don't sum to this thing, all right? Now, there are some misconceptions here. So some people will think, oh, is it because I fire so many electrons, right, that an electron that go through one interfere with electron that go through two? Okay, this interpretation is possible but not exactly correct. Alright, why? Because I can slow the electron gun to so slow, right, that only one electron fire at a time. And I will still produce this interference pattern, which means the correct interpretation should be as the electron comes out of the gun and has to pass through these two slits, right, it actually cannot function like a particle, because if it's a particle, it only pass through number 1 and or number 2. Then if the electron function as a particle, it only pass through number 1 or number 2, it cannot cause interference pattern, right? So it can only function as a wave. Then when it functions as a wave, I must represent the electron by a wave function, which is psi 1 and psi 2 as I pass through these two holes. Then the combination of psi 1, psi 2 is the wave function of the electron in this space here when I try to find out what happens when it hit the backstop, which is you can think of it as the screen, fluorescent screen, right? Or how the detector detects it. Okay, so, and that's the only way for me to explain this graph, right? So even one electron can interfere with itself, right? That is the conclusion that we get from this experiment actually. Okay, So this experiment actually illustrates that the electron can be seen to enter both slits as a wave and land on the screen as a particle. Right? Like I said, for me to produce interference pattern, I must function as a wave. I must be represented by a wave function. That means I'm a wave, right? But once I get detected by the detector, this is considered a measurement or an observation, which means that now I exist as a particle. And once I get detected as a particle, the wave function collapses. That means there's no more wave function already. Now I'm a particle. I completely exist at the point where I'm detected, right? Which is why in another experiment, right? Okay, this part you can follow, you follow, cannot follow, never mind. If I shine light here, while these two slits are open, right? Then the light tells me which slit the electron pass through, right? Then the electron behave like a particle and it doesn't produce this interference pattern, alright? Can? So that's quite amazing, right? So if you shine light here somehow so that you can see the electron passing through one or two, right? The fact that the electron is detected as a particle means it doesn't exist as a wave function, which means cannot produce interference pattern anymore. So it actually produces a graph that is equal to P1 plus P2. That's if I shine light here to detect which slit the electron pass through. Okay, again, can understand good, cannot understand, I think it's okay. Alright. Right, let's move on. Right. So I think this part we've talked about it. It's very similar to the light part. Alright, and I won't talk about it. Alright, so exercise 3 I'll leave to you to try. Alright. Please spend some time trying and then we'll discuss it in a moment. Okay, we're back, right? Hopefully you have tried this yourself, right? So the answer for this is that in the veritasium video, right, you should remember that the slit was like that. So this is delta x. So delta x was horizontal. So as you hit the screen, right, you realize that uh, the spreading of the light go from something like that to become something like that. It sort of smudges like that, something like that. Right? So it spreads more and more because as delta x becomes smaller, delta p of x become bigger. That means I increase my uncertainty in this direction and this direction. So instead of just focusing like that, I will become like that. Right? Or in other words, you can think of it as I diffract more. Alright? So if you look at this case, it's exactly the same thing, except in this case, the delta x is this one. Right, so as delta x drop, you should expect delta p x to increase, and therefore this one get broader. Okay? Alright, I'll leave you to copy the solution. Alright, you can pause and copy the solution. Right, then I'll move on. Right, I think question 4 is not very difficult. You can yeah, actually you should try yourself but I think if you look at it, you should realize by now that we discussed this, right? Nothing to do with the precision Heisenberg's uncertainty, right? Has more to do with this, right? Because delta x delta times delta p is greater than h, right? Finally, question 5, right? Please pause and do. All right, I'll come back in the next video to address question or exercise 5.